All right. Let f be a function from a to b and let s be a subset of a. The image of s under the function f is the subset of b that consists of the images of the elements of s. We denote the image of s by f of s. That is, f of s is the set of those elements t from B such that there exists an S in S with T equals f of S. So let's draw a picture to understand what's going on, right? So when you have two sets A, B, oops, okay, and a function from A to B, right? So what is the image of F? For every entry here, you are going to take it to somewhere here. So this might very well be pictorially understood. This is f of a. Okay, that's the image of a. Now if I have a subset S of a, then its image sits inside f of a. So somewhere here, pretend this is f of s. That's what image of s looks like. Okay. We may also use the shorthand f of s. This is capital f of capital S is the set f of s for every s in S. All right. One-to-one and onto functions. A function f is said to be one-to-one or an injunction if and only if f of a equals f of b implies that a equals b for all a comma b in the domain of f. A function is said to be injective if it is one-to-one. Okay. What is a one-to-one function? Let's imagine, okay, a set A and a set B, right? Venn diagram. All right. And suppose you have a function which maps from A to B. Okay. Now, once you have this, suppose you have two elements, any two elements, A and B. Injective function says if A and B are different, then their images have to be different. That is, if A goes here, then B cannot go to the same position. It has to go somewhere here. For every pair, their images have to be distinct. That's an injective function. Okay. A function that is not injective, well, you might be able to find somebody who goes to the same place as A. Okay. Then it is no longer injective. All right. As long as every pair goes to distinct images, you are injective. The moment you have two elements going to the same image, you are no longer injective. Remark, we may use quantifiers to express f as injective as follows. For all A, for all B, fa equals fb implies a equals b. Equivalently, for all A, for all B, whenever A is not equal B, we have fa is not equal fb. Here are some conditions which guarantee injective functions. A function whose domain and codomain are subsets of the set of real numbers is called increasing if fa is less equals fy whenever x is less than y. That is, you see, whenever for every x and for every y, x is less than y, implies fx is less than or equal to fy, we call such a function increasing. Likewise, what is strictly increasing? Whenever x is less than y, we must have fx is less than fy. So that is strictly increasing. So let's draw a picture to understand what's going on. You see, if you have a function from the set of real numbers to the set of real numbers, right? So if I have any x here, its value says here, right? This is x. Anybody to the right of x, right? So let me call him y. If I'm to the right of x, my height should be higher. In other words, I will be always increasing. All right. This is an example of an increasing, strictly increasing function. On the other hand, if I start stabilizing, then it's no longer strictly increasing, but it is increasing because it's not decreasing. Okay. That is, I am allowed less equals, you see. So fx has to be less equals fy. So the previous height has to be less equals the new height. That's all you require for a function to be increased. If the previous height is strictly less than the newer height, then you are strictly increasing. Okay. A function whose domain and codomain are subsets of the set of real numbers is called decreasing if fx is greater equals fy. So my previous height is greater equals my newer height. That is decreasing. If my previous height is strictly greater than my new height, it's called strictly decreasing. A function f from a to b, by the way, sorry, I forgot to mention here, a strictly increasing function is injective. A strictly decreasing function is also injective. Okay. Next, we'll talk about surjective functions. We'll continue in our next video.